Back to virtual LANs. Small question on ARP and MAC addresses and virtual LANs. The correct answer is C, but it's true that the histogram has considerably improved after discussion. What happens here? So what is the purpose of virtual LANs? The purpose of virtual LAN is to separate things, devices that are not on the same virtual LAN are not on the same LAN. Right? So how do two devices communicate if they are not in the same LAN? Through router. They use IP and there must be a router. So for A to talk to C, there must be a router between the two. Even though they're connected to the same physical switch, they cannot communicate because the physical switch is putting a stop between the two. That's the goal of virtual LANs, is to isolate. The fact that you happen to be connected to this wall socket that is at this floor doesn't mean that you can communicate with a computer that's connected to the same patch panel here. So the correct answer is neither A nor B. A would mean that we do an ARP request, well, that is if we are on the same LAN, and B is a variant of A, but as I said, the virtual LAN labels are not used by the devices. They're used only by the switches. In this figure here, when C connects to B1, if we do a Wireshark, we will not see the virtual LAN label. There's no need for it. But now B1 knows that C is in the red virtual LAN. So when B1 or S1 sends a traffic to S2 and to S3, for example, S1 will create a spanning tree, which in this case is simple. Here we need to know whether this packet is a red packet or a blue one. Because when a switch like S2 receives a packet here, it needs to know whether it belongs to the red LAN or not. Switches do learning and spanning tree, one per virtual LAN. So they need the labels for the traffic between the switches, but certainly not here at the host. So the hosts don't need to know their virtual LAN labels. In fact, what needs to happen is this. There must be a router somewhere that belongs to both virtual LANs if you want those virtual LANs to communicate. Right. Very often the router and the switch are the same physical hardware. This is just a piece of software here between the two. Or they are separate, depending here. So what will happen is you need to go through a router, as we know from the theory of IP. Right. So that's more or less the end of the MAC layer. We'll see a few legacy things. Legacy means things that are old and from the past, but continue to exist. IPv4 is legacy, if we want. Here is, if we adhere strictly to the world of layers, here is what we can call a bridge. A bridge is an intermediate system of layer 2. That means it's something that's sitting between two or multiple end devices and manipulates packets, forwards them in particular, only by looking at the MAC layer. We can have also physical layer repeaters that are intermediate systems of layer 2, right? Now, bridges can exist between different MAC layer technologies. That's the beauty of the MAC layer. Even if the formats are a bit different, we'll see an example in a minute why we need such differences. Bridges are able to communicate between the two. And from the viewpoint of terminology, the word LAN is a bit like other terms in this, like router, etc. May not always mean the same thing, but a LAN typically here means one subnetwork from the viewpoint of IP. When we put bridges between LAN segments, we have one bridged LAN, but the entire thing is one LAN. In some of the figures that I've used that are cut and pasted from the textbook that I otherwise recommend, the word LAN means a LAN segment. I left it on purpose because this is exactly what you will see in the literature. Those terms are not always well used. Like we do when we read software documentation, then the documentation is not always very clean. So here the same is happening. But for us, I think it's easier to remember that when we bridge several segments together, we have one single local area network. Remember, bridges, or the simple bridges, are transparent. If I have a device that is connected to other devices through bridges or not, there is no way to distinguish it by doing Wireshark, for example, by looking at the packets sent by a device, whether A is directly connected to B. If I connect two PCs with an Ethernet cable directly, without anything in between, or if I'm interconnecting by switches, the packets are the same. Of course, there are mechanisms to detect whether you're connecting to a switch, because a switch will react to a number of things that a host normally does not. But from the viewpoint of the MAC layer protocol, the Ethernet packet itself, there is no difference. So it's meant to be transparent. Also, the bridges are invisible to most of the tools we have. The tools we have are all IP layer and above. We do ping, traceroute, all that kind of things. The bridges are below that level. So with traceroute, we have the number of hops, which are the number of routers. But how many bridges there are in between, we don't know. We will not see it here. They are invisible. Wi-Fi is the most popular local area technology. It's a bit more complicated than Ethernet. For example, if you do a Wireshark of a Wi-Fi frame, you will see not 2 MAC addresses, source and destination, but 3, sometimes 4. 3 MAC addresses because there is something that is called the access point address. Here is an example. A very typical Wi-Fi installation consists in having base stations that are interconnected by Ethernet. So the base stations are connected by wired connections, and we make everything bridged. So this is the Wi-Fi base station is acting as a bridge. So we have one single bridge network. So if A now sends a packet to G that is sitting here, for example, you speak to your server that's on your wired Ethernet through Wi-Fi, and everything is bridged. The theory of the MAC layer says the frame sent by A should contain 2 things, source address A and destination address G, right? Because we're in the same local area network. That's one of the exercises we've done a few times by now. If I send a packet to a destination, I put as MAC address the MAC of the next hop, which is either the router or the final destination, if the final destination is in the same local area network as me. Here we have one local area network. So destination address will be G, and the source address will be A. Now, when we use the Wi-Fi protocol, you remember there are things like the RTS, CTS packets. Those RTS, CTS packets, the CTS packet, for example, is sent to the base station. So we need to know which base station we're sending it to. There might be multiple base stations. So here, this is used by having an intermediate system, which is called the access point address, which is also identified by a MAC address. So we will have that. It means the packet here must be intercepted by E. E knows it has to read the packet and put it on the Ethernet here. Right? If E would be a wired bridge, E would know it by doing the learning protocol and all that stuff. But here we do it explicitly because in Wi-Fi the communication is more difficult here. This is the normal Wi-Fi distribution system, base stations connected by Ethernet. Sometimes, if you want to do a cheap distribution system, you can interconnect your base stations by Wi-Fi. After all, the beauty of Wi-Fi is that we don't need cable. So if I'm renting a number of apartments and I put one Wi-Fi in every apartment and I don't want to pull Ethernet cables between the apartments, I can use Wi-Fi to go from one place to the next. It's a poor idea. It doesn't work well. Why doesn't it not work well? Because you have self-interference. The backbone links are interfering with the access link. When we do that, A here sends a packet to B. A is within range of its local Wi-Fi station M1. which M1 is in range of M2, but A is not within range of M2. So A sends to M1. The M1 relays it, like a bridge does. M1 is acting as a bridge, relays it to M2. M2 is connected to M3, and M3 to M4. So M1, M2, M3, M4 are bridges. Now what happens when A sends the packet here? On the air, it is creating a domain of collision around this system here. Nobody else can transmit here. Now, when M1 has to relay the packet, it uses the same base station, which is omnidirectional and uses the same channel. So it will prevent any other system from sending. And the same thing will happen here. M2 will do it, etc. So in the air here, in this region, we create a large number of collisions here. So the throughput of your Wi-Fi system is divided. Whenever you send one packet, in fact, in the air, you create a number of transmissions that will dramatically decrease the throughput here. Wi-Fi does not work very well from the viewpoint of performance. The way we found to make it work well is to have very, very large bit rate. So we run Wi-Fi at 100 or more megabit per second in order to make it work well. But if we have a large number of systems in all directions, the collisions are more difficult to handle than in the nice CSMA CD diagram of Ethernet that I showed before here. In such cases, we have not 3, but 4 MAC addresses here. Why 4? Because if I look at a packet sent from A to B, and I do a Wireshark here, I will say that it has destination address B, access point address M1, but at 2, so this is, we need 3 addresses here. At 2, we have similar thing. Here we have a packet sent by M1 from M2 to M3, but the CTS RTS things needs a source and destination MAC address of the CTS RTS thing, which is happening between M2 and M3. So we need also the addresses of M2 and M3. So at the end, we have 4 MAC addresses in a Wi-Fi header. Question?
Does the interference also apply if they're not bridges, if they're just Wi-Fi routers based in Wi-Fi?
If there would be routers, it would be the same. At least in this case, if the configuration is this, it would be the same.
So for example, if you have multiple rooms that are near and each one has a router, you're negatively affecting your performance?
Yes. The question is, are you negatively affecting the performance? The problem here is not so much whether we are routing or bridging. If the only path that exists from A to B is this one, then routers or bridges will calculate the same path, because that's the only one that exists here. So the same thing will happen regardless of routing or bridging. So if you have multiple base stations and you interconnect them wirelessly, you should expect that the performance will be dramatically less good than if you interconnect them with wires here. Right. Now, if you have only 2, 3 devices and you need to extend range, it can still be useful. Sometimes we read, in particular in the industrial environments, in smart grids, for example, we read, and in industrial automation, we read non-routable protocols. What does that mean? Well, it simply means things that have been developed directly on the MAC layer. After all, if I look at the local area network, if I'm building an industrial system that has a number of machines that need to be controlled, that need to talk to each other, if they use the MAC layer to do that, well, the MAC layer is a networking layer. So they can communicate. And what people have done in the industry environment, they have built their own software world directly on the MAC layer, without TCP, without UDP, without IP. So you can imagine that everything we do with TCP and IP, we can do it directly over MAC. If I send a packet from A to B, TCP, as we will see a bit later, will repair the losses, for example, will number the packets in order to detect which one is lost. You can do that directly by sending the packets in the MAC layer. Those things exist, and they are typical, for example, of smart grids. Even in information systems, we had things like NetBIOS that did it before. Here, this is the sampled value protocol that, for example, is used between a server that collects all the information and a device that measures things. This is, if you buy such a system today, probably by default it will be doing it directly on the MAC layer. It's called non-routable because there is no IP, which means if you have more than a small number of devices and your bridge network is becoming too small, you cannot put IP routers in between because there is no IP in the software here. This is why it's called non-routable protocol. They tend to disappear. They tend to be replaced by the same software in which we put a socket interface instead of the native socket that was run here. Let us conclude with, or not conclude, but let's move on with one question here. I am in one of those hybrid LANs where I bridge between Ethernet and the base station. So here I have one Wi-Fi network, and I have a bridge, which is a device that has a Wi-Fi antenna, so it connects to the base station, acts as a bridge, and connects the rest of my installation here. If I look at the MAC destination address sent from the web server to LAN, what MAC address will I see? And the majority says D, which is the correct answer. It was a short race between C and D, surprising. Obviously, I mean, this is one big bridge LAN, so the destination address in the bridge LAN is always the MAC address of either the next hop router or the destination if it's in the same LAN. IP says if it's on link with you. So the correct answer is D here. Same question now. Assume I'm trying to be a bit smarter. Instead of having a Wi-Fi link between my Ethernet switch and my base station, I pull an Ethernet cable from my base station. All base stations normally have an Ethernet socket, so I do that. Same question. And the answer is, well, it's the same here. So there is no difference, of course. A few words about security. So MAC addresses are sent in the clear, right? So it means there's lots of things you can do. You can, if they're sent in the clear, you can observe what's happening. So you can gain information on who is talking to whom, at least with the MAC addresses. You can also do free riding. You can connect yourself to this network. And worse, you can do impersonation. You can pretend to be someone else. We've seen that with ARP in particular. But also you can use ARP, or you can simply impersonate someone else's MAC address here. There's a number of solutions. Essentially, there are two types that they all fit into what is called MACsec, MAC layer security, which consists in using encryption, adding a layer of encryption. So when I showed the Ethernet packet format, in addition to that, we add a layer of encryption that will encrypt and authenticate all the Ethernet headers. This is typically done only on Wi-Fi. MACsec exists on paper for Ethernet, but in practice, as far as I know, it's very seldom done on a wired system. But on Wi-Fi, it is done. So it uses encryption in the sense that the MAC frame payload is encrypted, so it's not sent in the clear that I showed before, but we send a number of words that help to know which encryption system is used, and then the frame that is sent is encrypted, using keys that are negotiated when you connect to the base station. So when you come to EPFL in the morning, you connect to the base station. Then in order to connect to the Wi-Fi network of EPFL, you need to have some credentials of some kind. You need to, if you're on the EPFL or EduRoam network. So you are authenticated, and when you do that, there is a negotiation between the infrastructure of Wi-Fi that's behind the base station and your device, which results in an agreement to serve you and an agreement on a number of shared secret keys that will be used for some amount of time. Those keys will be used to encrypt all the traffic and also to authenticate it. So when the base station receives a packet, the packet is authenticated. The source MAC address is authenticated, is the one that corresponds to the guy who gave the credentials in the morning. So if someone else comes and wants to connect to a PFL and using Wireshark or whatever copies a number of fields and repeats your packet hoping to be able to create other packets, this will not be possible if this other guy does not have the shared secret keys that you have received from the Wi-Fi infrastructure. So free riding will not be possible, and also impersonation will not be possible. It will not be possible to send new packets that pretend to come from your address here. At home, you probably don't have the same kind of encryption. Typically at home, you have a weaker form of encryption, of access control, where all you need is to have a secret, to know a shared secret, what is the password of your Wi-Fi installation. This is weaker in the sense that anybody who knows the secret can participate and can pretend to be you, for example, but someone who does not know the secret cannot read your traffic and cannot also insert traffic, at least if you use that type of protection. On Ethernet, there is no security today in most systems here, other than what we have discussed already when we discussed ARP, which consists in the switches observe all traffic, and if they see things that are strange, like for example, a lot of different MAC addresses that are coming from the same port, then they will start to complain. Because at EPFL, it is EPFL that normally makes the switches. You're not expected to create your own LAN connected to Ethernet. So let's do a little homework and analyze what happens. So assume Bart, who is a regular EPFL student, wants to have his sister, Lisa, connect to EPFL as a free rider without being authorized to. And since Bart took the TCP-IP course, he knows how to set up his laptop as a bridge. Here. So he will bridge between, he connects to Wi-Fi here, and through an Ethernet connection, connects to Lisa, and runs here as a bridge between Lisa and the campus here. Will it work? The majority says no, and it will not work. That's correct, it will not work. If this is a bridge, well, it looks smart because you have only one IP address, so we cannot make it as a router because we would need a different IP address for Lisa and Bart, and we get only one. So bridge looks smart. However, we know that when Lisa will send a packet, the source MAC address will be Lisa's stuff, so it will not contain all the authentication layer that is expected by the Wi-Fi base station. Therefore, the Wi-Fi base station will see that this packet is coming from nowhere that looks authenticated to me, so it will discard it. So that will not work. Question?
So could make it work if it was NAT instead of a bridge?
Perhaps, who knows? In fact, that's the next question. So Bart, who never gives up, tries something else, configures his PC as a NAT. And now probably it will work. We still need to test it. I mean, but in principle it should work, because when we operate as a NAT to the rest of the world, here to the WAN part of the NAT is now the Wi-Fi part here. To this part of the world, it is as if Lisa would be a different process on this machine. It's just a different program running on the same machine. So it's perfectly legitimate. You can have your device that connects through different processes to different sites, for example. So it will work. Here, the NAT will take all the traffic, will encapsulate it as if it would be coming from this machine, and therefore it will work. Right? So that's one of the beauties of NAT, but it shows also the weaknesses of authentication and access control. Right? Voilà, that's the end of the MAC layer. Not the end of today's lecture, because we're a bit early, but we will start the transport layer in a minute. The MAC layer, I think, originated as a shared medium protocol, and we find that a lot in the architecture of the entire IP itself, but is today essentially made of switches when it's on a wired system. We have seen that we can build networks with switches, or with bridges, or with routers. What is the difference? Yes?
Bridges and switches connect networks into one, while routers connect separate networks for them to communicate.
So bridges connected several things into a same network, whereas routers connect several networks. It's true, but that is a tautology. In a sense, it's the definition of what we call a network. So it's true, it's formally true. But now if I take a purely practical viewpoint, I have to interconnect a number of devices, laptops, computers, handheld devices, printers. Should I need bridges or routers? Depends if you need wireless or not. No. Routers work with wireless. Yes, I mean, the wireless is a physical layer technology. MAC layer is a way to interconnect it, and no, that doesn't make a difference. It's a concrete problem. I mean, if you're building a smart grid, for example, you can use it at the MAC layer. We've seen that some protocols work only at the MAC layer. You could also do it at the IP layer. What would be the difference? Yes? With just a bridge, we will not be able to connect. But again, that's the definition of a bridge. So why do we have that? Why is not the internet built with 1 million bridges? And why are we not, the whole world, on one big LAN? We're one big family, we're on one big LAN. It will be congested, so it's a scaling thing. Layer 2 does not scale to large systems. The largest layer 2 network that I have ever seen in history had 30,000 nodes, and it was using extremely sophisticated layer 2 technology called token ring bridges. With Ethernet, you cannot do that. It's where you will have scalability problems.
The scalability problems come from the spanning tree. Is that correct?
The scalability problem comes from a number of things that derive from the assumption that a LAN has been built as a local stuff, so not too large. Because of that, we do a spanning tree, for example, but also we learn the traffic, we flood things when we don't know where to send. So imagine if the internet would be used, whenever there would be one bridge somewhere in Australia that doesn't know where to send the packet to the printer that is next room, it would flood it to the entire world. And then all packets in the world will learn that this address is coming from that thing in Australia. This is how it would work, right? So the flooding, the use of flooding, is typical of something that will work only for small scale. There is also the tables that are unstructured. Imagine you are in this nightmare where the backbone of the internet is using bridges. You are one of the backbone bridges, and you have to forward one packet. You need to look up a list of MAC addresses, practically all MAC addresses in the world, right, for every packet. So that also would not scale. So there are a number of mechanisms that would clearly not work. So the difference is scalability. Bridging is convenient because it's plug and play, no configuration. It will work for things that are small to medium size, but it will not scale to the world here. That's the take-home message here. Voilà. Are there any questions? Then, without any further transition, we move on to the next chapter, which is the transport layer. Good question. Is that included in tomorrow's quiz? No. So my plan was to finish the MAC layer today, but sometimes we are early. That happens in life. In Switzerland, it should happen a lot. But no, it's not on the program of tomorrow. We will not see much anyhow now. We have seen already the transport layer. There will be the topic of Lab 3, where in the Lab 3 you will be doing application programs. As application programs, you will use the transport layer. And so you will have to learn what is the difference when we use UDP or TCP. And then what is less visible to the programmer, but we will use here, we will see in class here, is how TCP works, where TCP is encapsulating a lot of the complexity of the internet, in fact. We will do it in 2 phases for TCP, because TCP does 2 things. It does transport layer function, which I recall is the job of the transport layer, is to serve what we will do in Lab 3, is to ease the work of the programmer. Instead of programming directly on the IP packet, you have an abstraction that is easier. This is what the transport layer is doing. And TCP in particular takes care of packet losses, which are very annoying if you had to do that in every program. TCP does another thing, which is called congestion control. TCP is responsible for making sure that the internet does not collapse because of congestion. Now, why is it in TCP? We'll talk about it a bit later. That function is in the transport layer, although it is in fact a function that has to do with the traffic regulation of the network layer and also of the MAC layer, because you're trying to avoid having too many losses in the queues of bridges and routers. We'll talk about that in another module, which is called congestion control. So right now we will do only 1/2 of TCP, which is all functions of TCP except congestion control, because they are intellectually very different. The good news is that there is only one TCP, so I said IPv6 is really a different networking, a different network layer. It's not exactly true. It's not like if you had AppleTalk and NetBIOS, which are 2 radically different elements of software and nothing works together. TCP is the same for IPv4 and IPv6. So there is no TCP-v6. So the theory of TCP is the same. The practice is not the same, though. You will see in Lab 3 that if you do a program that works with IPv6 only or with IPv4 only, the program might be a bit different. So the software might be different, even though the protocol itself is exactly the same. TCP is exactly the same here. But right now we'll talk about UDP, and the thing we've seen already when talking about NATs is ports. We've seen that NATs use port. That's the trick of NATs. NATs would not exist if there would not be port numbers. Port numbers are numbers, those are the addressing information of the transport layer. So the transport layer is end-to-end. Normally, the mental model of the internet is the transport layer exists in 2 entities that communicate, if it's unicast communication. A speaks to B over a network. The transport layer is only in A and B. It's only in the end systems as a first approximation. But still, if A talks to B, usually in A and B, there is not only one thing that is speaking. If there would be only one thing, we would not need port numbers, but there may be multiple things. For example, this device may have a process that is a DNS server, and it may have also a web server, and it may have other things that are happening here. So for that, UDP uses the concept of port numbers, like 53 is one, 1267 is another one. In order for some program to talk to another program, they need to use ports number. You cannot have program A speak to program B. Before doing that, you need to choose which port number the source and the destination will use, or the 2 ends will use. Some of the port numbers are well defined. For example, if you are a web server, a DNS server, you expect to be using UDP port number 53. If you are using a web server, you expect to be using TCP port 80. Although you may change that by specifying the port number in the URL, as we will see some examples here. The source port number is used to be able to distinguish several processes. For example, you might have in an application multiple processes that are talking to the same or to different processes on the same machine. Typically, that does not happen a lot, but it may happen a lot. So the port number is only 16 bits, which is even very large, because we have seen it's so large that NATs can reuse it. And this is essentially the only thing that is contained in the header if you use UDP. So if you use UDP, UDP is the simplest of the transport layer. It does almost nothing. It simply allows you to specify port numbers. So if we do a Wireshark or a trace route of something that is using UDP, we will see a UDP source port, this one, a UDP destination port, and two other things. One is the UDP message length, that is indicating what is the size of the entire message. In principle, it fits in one packet, but as we will see a bit later, a UDP message may be broken into multiple packets, in which case it is the size of the entire message, not the size of this packet here. And the checksum. We've seen checksum when we spoke about the Ethernet header, the Ethernet trailer. Here it's a bit similar, although it's a very weak checksum. It's not sophisticated coding. It is using simply parity modulo 2 to the power 16 minus 1. So it is a weak checksum that is able to detect single-bit errors and a few other things. You should not rely on it for make the integrity of your system, but it will be useful to detect a number of losses here. I said UDP is very simple. At the same time, it's fairly powerful in the following sense. UDP is message-oriented. We've already mentioned that. It looks fairly obvious, but it means that when we send one UDP message, we don't need to do start of message delimiter. We don't need to have, like we had when we saw an Ethernet frame, we don't need to have something that says, now this is the beginning of a UDP message. The fact that you receive a UDP message means this is one message sent by the source. The source sent it as one message. A UDP message can be that large. IP packets are typically not as large. So it may be that one UDP message needs several packets, in which case it will fit in several packets. If any of the packets that is lost, what do you think will happen? If I have a message that needs 4 packets, UDP sends it into 4 packets, and packet 3 is lost. What will happen at destination? The application layer has to detect and fix it. But what will it fix? Will it... this packet or the entire message? The whole message. So the key thing with UDP is message-oriented, means you send an entire message. If anything goes wrong, the message is lost entirely. Voilà, and that's all for today. See you tomorrow.